Hi everyone, today I would like to present our ongoing project, Semantic Conflict Detection for Transactional Data Structure Libraries. I'm Yaodong Sheng, a PhD student from Lehigh University. The focus of this project is on transactional data structures. The problem that transactional data structures tries to solve is composition. In traditional concurrent data structures, our goal is to get individual operations to take effect atomically. In transactional data structures, we want a sequence of operations on a set of data structures to take effect atomically, which means either all of the operations happen or none of the operations appear to happen from the perspective of other threads. In this example, we have two lists, L1 and L2. Each thread is trying to update both lists, but the control flow depends on the state of the lists. We want each thread's entire set of instructions to appear to happen indivisibly. So, for example, it is okay for T1 to completely happen before T2, in which case the final state will be that L1 is empty and L2 has the values 4 and 5. It is also okay for T2 to happen completely before T1, in which case the final state will be that L1 has the value 4 and 5, and L2 is empty. However, traditional concurrent data structures don't provide composability, which means that individual operations issued by each thread can interleave with those of others. As an example, without support for composition, we could wind up with a result like the one on the bottom right, where L1 has the value 4 and L2 has the value 5. As a brief reminder, with transactional memory, programmers can use existing data structures. They wrap their accesses to those data structures in language-level transaction, and then the compiler and hardware work together to make all loads and stores within the region appear to execute as an atomic operation. This makes it very easy to verify correctness, but it is hard to get good scalability. The main problem is that every memory access in transaction can be a source of conflicts, even after it has stopped being useful to the transaction. In the TDSL approach, special transaction-aware data structures are used instead. They have a more complex interaction with underlying transactional system. These data structures are harder to write, but they can be optimized so they give good performance. As an example, when traversing a long list, transactional memory will abort if head changes. With TDSL, once the traversal has moved past the head, it need not abort if other transactional modifies the head node. Prior work devised strategies and optimizations that provide very good performance for a handful of data structures. Our goal is to elevate these ideas to a general-purpose methodology. We want a methodology that can do all of the following. First of all, we want to give programmer the ability to easily iterate through arbitrary data structures. Also, we want to support in-place modification of objects stored in a collection. We want to be able to support arbitrary data types. This needs to include types that cannot be read in a single atomic hardware instruction, and types whose range is infinite, like strings. Lastly, we are aiming to create an approach that is robust and generally applicable to a wide variety of data structures. For example, we want to be able to resize a hash table without aborting operations that are using it. Our brief announcement only focuses on a few aspects of our design, which is still under development. In the remainder of this talk, I will discuss two things. The first is that there is tremendous opportunity if we use transactional memory as a low-level synchronization technique inside of individual data structures. To illustrate why this is powerful, consider how hard it is to make a scalable doubly linked list using just compare and swap. But when we build data structures with unidirectional links, we end up adopting overhead that hurts scalability. Using TN makes it easy to have a doubly linked list, and that lets us avoid such overheads. TN simplifies reasoning about correctness. It naturally supports speculation and rollback for those cases where we need it. It can provide memory safety, so we don't have to rely on garbage collection. These slides illustrate a thread removing value 6 from a list. Since the operation is part of the large transaction, we can't just remove the value right away. We have to wait until the transaction commits. So with singly linked list, if thread 1 wants to remove 6, it puts 5, 6, and 8 in its reset, and it puts into its write set that at commit time, it must make 5.28. But what if there is a concurrent insertion of 7 into the list? That thread will put into its write set that at commit time 6 will need to point to 7. Suppose that thread 2 commits first. Now 7 is in the list. That in turn means that sequence 5 point to 6 point to 8 is no longer valid. When thread 1 tries to commit, it sees that 6 successor changed, and therefore it cannot remove 6 because it would be invalid to make 5 point to 8. When we have a doubly linked list, thread 1 doesn't have so many dependencies. It can record that it should remove node holding 6 without caring about the predecessor or successor. In our design, the thread also marks the node as pending delete. Other threads can traverse through the node, but they cannot use it without conflicting with thread 1. Suppose again, then thread 2 wants to insert 7. We can simply add it and then mark it as pending insert. As with pending deletion of node 6, threads can traverse through node 7, but they cannot use it without conflicting with thread 2. When thread 2 commits, it will change the state of 7 to present and give up its ownership of the node. Then, when thread 1 commits, it can locate the predecessor and successor of node 6 and use them to atomically unstage 6 from the list. In the previous example, we made ourselves oblivious to structure of the list. 6 wasn't in the list because 5 pointed to it. It wasn't structural property, it is an semantic property of the list. What about when a value is not in the list? In past work, there was only one solution, structure. In the top row of the slide, we can say that 62 is not in the list because 60 points to 64. In our work, we add two new ways to manage non-existence. First, we introduce range nodes. They can express that elements are not in the list. For example, in the second row, we have a node that indicates that the range from 60 to 64 exclusive is not present. The third row shows that we can use an out-of-band table to express non-existence. A low-level transactional memory transaction observed that 60 points to 64 and that the table entry corresponding to 62 had a value of 42. If an insert of 62 is guaranteed to also increment 42 to 43, then for as long as the value remains at 42, we know that 62 hasn't been added. It is worth noting that all three ways of representing non-existence are useful. The table is an effective way to represent that a lookup could not find a value in the list. The range node is an effective way to handle when the prefix and suffix of a range operation is not present. And the structural technique is useful when there is missing elements within a range. In this slide, a range from 18 to 46 can use range nodes to mark its boundaries. This ensures that adding 14 or removing 50 won't cause the range to abort. At the same time, it doesn't make sense to put a range node between 20 and 30 or between 40 and 50. In those cases, we use structural information. Meanwhile, a failed lookup would use the table from previous slide. To wrap up, I want to emphasize the main idea in our work, which is that separating semantics from structure is a promising strategy for building scalable, composable data structures. It avoids false conflicts, unnecessary aborts, and wasted work. It also enables better composition. For example, we recently completed a design for a concurrent hash table that can be resized while threads have pending transactions on it, without incurring any aborts. This is only possible because we are able to separate semantics and structural conflicts. If you are interested in learning more about the project, please don't hesitate to contact me. Thanks.